Hello, and welcome to probability lesson 2 here on independent and dependent events. So today we're just going to talk about how we calculate probability. Well, first of all, how we determine independent and dependent events, and then also how do we calculate probabilities of independent and dependent events. So this is a fairly easy concept, just nothing too tricky here. Again, working with just kind of basic probability concepts here. So the first thing we're going to do is define what is an independent event versus a dependent event. And so first of all, an independent event, and this is an independent event here. Independent event is two events where the occurrence of one does not affect the occurrence of the other. So meaning whatever I do in the first event really has no implications for whatever I do on the second event. So if I were to, let's say run a sprint or something like that, and then I was supposed to throw, discus or something like that, it wouldn't matter really how well I did in the sprinting event, on how I might do on the throwing event. So those would be independent events. But in terms of probability, you might be talking about something like rolling a dice and flipping a coin or picking a card out of a deck. And so we'll talk about what that means. But if I were to pick a card out of a deck and then roll a die, whatever I chose, if I chose a queen or something like that, wouldn't have anything to do with, what I would roll on the die. And so those are independent events. And a dependent set of events are two events where the occurrence of one event does affect the occurrence of another. So this is where whatever I do in the first event will make a difference on the probability of something happening in the second event. So this could be, it's usually when you're working with the same thing. So if I were picking a card, this is what makes card counters and people that do well, like in events in Vegas, is they can count cards because there's only one card. If they see a jack of clubs get pulled, they know that jack of clubs is never going to show up again, and so they don't have to think about that. So dependent events is if I were to do something and then that changes the probability of the second event happening because of what happened in the first event. So it depends on the first event what happens in the second event. So we're going to make some very simple examples here. And so here you have like a box. We're going to tell whether this is independent or dependent. You have a box of granola bars containing an assortment of flavors. You randomly choose a granola bar and eat it. Then you randomly choose another granola bar. So event A would be I choose a coconut, and it's almost, it's supposed to be almond. You choose a coconut almond bar first, and then you choose a cranberry almond bar second. Now, the reason why, and I'll say this is going to be dependent, is because when I choose the coconut almond bar and then eat it, and I go to choose another bar, the second bar now has changed the probability of getting it because there's one less bar. I ate one of the bars, so that coconut almond bar is gone. It's not factored into the probability anymore. So when I go to get the cranberry almond bar, it has changed because there's one less bar in there. And so you can see how the probability of the second event happening depends on what I did in the first event. Now, if I had taken that coconut almond bar and I was like looking at it, I'm like, this doesn't look really good, and I go to put it back and then choose a cranberry almond bar, then it becomes independent because I put the bar back. So when I go to choose my second bar, it doesn't really matter what I chose the first time because I put it back. So that's the key there is taking something and not putting it back makes it dependent. Here, you roll a 6-sided die, so your normal die, and then you flip a coin. So the probability of getting a 4 when rolling a die, and then the probability of flipping tails when you're flipping a coin, these are going to be independent events because it doesn't really matter what I roll on the die. It has no impact or implication for whatever I'm going to get in the coin. So whether I roll a 1 or 2 or a 6 or something like that really has no bearing on what I'm going to flip on my coin. They are independent events. They don't depend on one another, if you want to say that. So how do we calculate the probability of these two types of events? Now, an independent event is pretty basic. The two events, A and B, whatever they are, you figure out the probability of each one. And so it says the probability of both events happening. The key word here is both events occurring is the product of the probabilities of the events. So if we are saying, for example, this 6-sided die and the flipping of the coin, the probability of rolling any given number on a die, since there are 6 numbers, is 1 out of 6. The probability of flipping any side of the coin, since there's only 2 sides on the coin, is 1 out of 2. So I would simply just find the product of, and I'll underline it here, the product of those probabilities. So 1 out of 6 for the die, 1 out of 2 for the coin, and I could just multiply them because that's what product is. It means to multiply. So you just take, so how we write this is the probability of A and B happening equals the probability of A times the probability of B happening. Pretty straightforward. If I want to know if there could be more than 2 events, you could have, what's the probability of 4 different things happening? You would just have to multiply all the probabilities of those happening, and that would give you the probability of all of them happening in that sequence. The probability of dependent events is slightly more complicated because the probabilities change because one probability is dependent on the other. And so here, it's the same idea in that you are still going to find the product of those probabilities, but you have to understand that the probability of the first event is one thing, but then you have the conditional probability of the second event given the first. Because what happened in the first event changes the probability of the second, we have to take that into account. So how we write this is, and you don't need really to know how to write this, you just need to know how to calculate it. The probability of A and B happening is going to be the probability of A times the conditional probability, which how we write that is B, the probability of B given A. And that's supposed to be more of a vertical line there. So this will make much more sense when we actually look at some events here. So note the probability that event B occurs given that event A has occurred is called the conditional probability of B given A and is written as not probability of B given A. So that's the math language there that is written. This will make a lot more sense when we actually do some actual examples here. So here's a set of events, and we're going to calculate. First, we need to understand whether this is going to be independent or dependent. So as a part of a board game, you're going to need to spin the spinner, which is divided into what looks like 8 equal parts. Find the probability that you get a 5 on your first spin and then a number greater than 3 on your second spin. First of all, we have to determine whether this is independent or dependent. Does it matter what I spin the second time? Does it matter what I did the first time? No, because when I go to spin it the second time, there's still the same probability of getting any of the numbers is there. So I didn't remove a number or something like that. So this is going to be an independent event, and so we're just going to simply multiply the probabilities of each one happening. So you do this one at a time. So we're going to first do, you get a 5 on your first spin. Since there are 8 numbers, the odds of getting any one of the 8 numbers, like a 5, is going to be 1 out of 8. And so we have 1 out of 8. And we're going to multiply that times the probability of the second event happening. Now, a number that is greater than 3, well, greater than 3, 1, 2, 3, 4, 5. There are 5 numbers that are greater than 3 out of the 8 total numbers. So the probability of getting a number greater than 3 would be 5 out of 8. And so we simply just multiply those numbers. And remember, when you're multiplying fractions, you multiply straight across. 1 times 5 is 5. 8 times 8 is 64. And you would reduce those fractions if you could, though 5 out of 64 doesn't reduce. So it makes sense that the probability is significantly lower because you're asking the probability of multiple things happening. The probability of those things happening just like that is going to get lower the more events that you add. Here we have a bag containing $1 bills, or 20 $1 bills, and 5 $100 bills. You randomly draw a bill from the bag, set it aside. Okay, there's a key word there, set it aside, I'm not returning it. And then randomly draw another bill from the bag. Find the probability that both A and B will occur. So you have event A. The first bill is going to be a $100 bill. And then event B is, the second bill is also going to be a $100 bill. So first of all, we need to find the probability of the first event happening. We can see here that there are 20 $1 and 5 $100 bills, which means that we have a total of 25 bills in this bag. So the odds of pulling a $100 bill, since there are 5 $100 bills, is going to be 5 out of 25, because there are 5 $100 bills out of the total of 25 bills. So we're going to take that and we're going to multiply. Now what happened here, though, is that we set this aside. We did not put it back. So there is not only one less $100 bill, but there's one less bill in general. So now I don't have 5 $100 bills. I have 4 $100 bills. And I don't have 25 bills. I now have 24 bills. So this is that conditional probability that you have to take into account when you're dealing with dependent events. So to draw another $100 bill, there is one less $100 bill now, since I've taken one out and not put it back. And there is one less overall bill, so 4 out of 24. So those are the odds of doing that. And so again, we multiply these, again, straight across, 20 out of, and then 24 out of 25. I want to say that's 600. Now I'm going to doubt myself here, but I'm pretty sure that 25 times 24 is 600. It is. And then we can reduce this. This is going to be 1 out of 30 if reduced. So the probability of getting both of those bills being $100 bills is 1 out of 30. You randomly select 3 cards from a standard deck of 52 playing cards. What is the probability that all 3 cards are hearts? This is going to be 2 different setups here. One, you're going to replace each card before selecting the next card. So that's the key there. You're replacing it. This makes it an independent event here. So I can just simply multiply all the probabilities. Now, you have to know something about cards here. And it tells you that there are 52 playing cards, but there are 13 of each suit. Since there are 4 suits, hearts, clubs, diamonds, and spades, 52 divided by 4 is 13. There are 13 of each suit. So hearts, if I'm drawing a heart, 3 cards are hearts, and I'm replacing it each time, there are 13 out of 52, which, there are 4 different suits. So you could really just reduce that to be 1 over 4. I have the probability of getting a heart, since there are 4 suits. You could divide it by 4. 13 out of 52 still reduces to 1/4. But then I'm going to replace it each time, so the probability is not going to change. The probability of getting a heart 3 times in a row is going to be 1 out of 4 times 1 out of 4 times 1 out of 4. And then, so when you do that, 1 times 1 times 1 is 1. 4 times 4, 16 times 4 is 64. The odds of getting 3 hearts in a row drawing cards is 1 out of 64. So now let's do this when we do not replace them. So like literally getting 3 hearts in a row and keeping them. This one's a lot more going on here because you're reducing. Now, remember that there are 4 suits, so it's 13 hearts out of 52, or 1/4 times. Now, let me change this actually to be what it's supposed to, with the full fraction here, so it's easier to see. There are 13 of each suit. So the first, when I go to draw the first card, I have a 13 out of 52, or 1/4 chance of getting a heart. But I'm not going to put that heart back. So when I go to choose a heart, try to choose a heart again, there's 1 less heart, but then also 1 less card. And then when I go to choose the heart again, there's 1 less heart again, and 1 less card again. So when I go to multiply this, we have, let's do this multiplication here. 13 times 12 times 11, 286 out of 52 divided by 51. 52 times 51 times 50, 2,550. I don't know if that reduces, though. You could put that in your graphing calculator and check, and that's actually what I'm going to do right now. Hang on. Remember that in your graphing calculator, you can reduce fractions very easily by using the alpha y equals function. If you go to alpha y equals, that'll bring up your function or your fraction menu. And so I can just type in 286 over 2,550, and it does reduce the fraction for me. It doesn't reduce it much, but it is 143 out of 1275. So, oops, kind of skewed there. But that is the reduced fraction. So to find the conditional probability here, this is, again, this is just math equations here, or math jargon, I guess you could say. It's not really necessary that you know this, but the probability, conditional probability is that B will depend on A. And so what that is the probability of A and B happening over the probability of A happening. Again, that is just the math jargon. Again, it's probably going to be so much easier for you just to understand what you're doing here. And it'll be, you won't even think about that probably at any point. So you don't need it. So let's look at these examples to find conditional probabilities. So you have this table that's over here is the quality control inspector checking for defective parts. The table shows the results of inspector's work. And so over here, I know this kind of got cut off, and I apologize, but we can see that the total, if we run the total this way, the total defective parts that they inspected, it looks like it's going to be 39. The total that the non-defective parts are, looks like it's going to be 461. You could also look at it the other way and see how many failed and how many passed. It looks like of all the parts, 453 passed, and you can go this way as well, and that all of the failed parts totaled would be 47. You want to make sure you are looking at that and you're totaling those up both ways. And you can also double check The combination here and the combination over here should be the same. 453 and 47 is 500, but 39 and 461 is also 500. So just to make sure, the 500 really doesn't mean anything, but you just want to make sure you added them right. They should add up to be the same. Whether you're adding one way or the other, the totals should be the same. So when we look at the probability of a defective part passing, what we need to look at is a defective part passing, the probability of a defective part passing. So we don't look at it out of this 500 over here. You look at the defective part, and then you look at the passing. Okay, defective part passing. The odds of a defective part passing, there were 39 total defective parts. 3 of them passed, so the probability would simply be 3 out of 39. One thing that I did not, and based also that I think reduces to 1 out of 13. I don't know why I'm even looking at this, but I just want to make sure. I hate making mistakes on videos. It is 1 out of 13. One thing I forgot to mention too is you can express these as percents. So if you like expressing, and sometimes you may see the answers given to you as a percent probability as opposed to like a fraction or a ratio. So if you divide them simply, you get 0.0769 or 7.69%. So you can write these as percents as well. It doesn't really matter. I'm just understand you may see them both ways. So now we have a let me get rid of those highlights, a non-defective part failing. So now we're looking at non-defective parts here, and we're looking at the non-defective parts that are failing. So 11 failed, and there were 461 total non-defective parts. Just 461. That is not going to reduce. 11 out of 461 doesn't reduce, but we can, again, I told you guys that you can express these as percents as well, which looks to be at 2.39%. Either one is acceptable. The last example here, at a school, 60% of the students buy school lunch. Only 10% of the students who buy lunch also buy dessert. So you have 60% of the students buy a school lunch. 10% of the students who buy lunch also get a dessert. What is the probability that a student who buys lunch also buys dessert? This is kind of sounds confusing, but it's way easier than you think it might be, and that is simply because the second part here is that they buy lunch, and you already have the probability of them buying lunch, and you have the probability of them buying lunch and dessert. It really is just as simple as, well, since 10%, doesn't really matter what the number is of students, but 10%, we can just say 10 out of the 60. And it's really that simple there, which is 1/6, which you can change to a fraction as 16.67%. Either one is acceptable. And that is it. That's independent dependent events.